start streaming, and then we hope that this thing works. Yeah, I think you can unfreeze it once it's done the code. I think a more stable connection is you can. Please. Yep. Okay. No, I think it's good. Yeah. So full screen, and then yeah, the stream seems to be working, and yeah, I'm sure you know how to use it. Just like
How do I erase?
I think like oh yeah, this stuff here. So like, you know, if you're gonna write that, yeah, okay. Oh my god. Oh no, don't use this one. No, that's like you write and it will convert to text. So don't do that. Which one? Oh, I just hooked it. I need like reinsert the thing again. Guys, I don't know how to use technology. I'm a third year. Even though I do comp sci, it's embarrassing. Okay. Okay, it should load up. Nah, okay, like I'm sure you guys will figure it out. Just don't get pissed by the technology.
How do you write on that screen? It's like, or you can fold it up.
You can fold it up. Just like you're gonna like, please do not crash. Okay, yeah, good. Yo, good morning, or should I say good afternoon? Yeah. You're just in time because I think we can start.
Wait, how do I fold this up?
Huh? You just fold it.
You literally just fold it.
You really just fold it.
I put it on the keyboard.
Huh? Yeah. Sure. If you like, just put it on the keyboard.
Just stuff.
It's fine. It's a test of technology.
The cable's too short.
What?
The cable's too short.
Should work. Yeah. Okay.
Has everyone scanned attendance?
Yeah. You too. The came in.
Color. Wait, let me test this.
$4.
What? How does this work?
Use that one. Wait.
That's white.
Yeah. Change that.
What the heck? No, that's moving the whole screen.
Yeah. We need help. Huh? Yeah.
Wait, why is there a keyboard here?
Yeah. Okay, that works.
Where's the eraser?
I think. No. Wait. Sure, you can. Okay. This first one.
The first one is eraser.
The first one. Yeah. You're up there.
So not used to this.
Yeah. I mean, you can lift it up like this, or you can like put it down. Up to you. Whichever one works for you.
How do I change the thickness? Oh, there we go.
So if I come back to this and like I just see a broken laptop in the side. Cool. Under file grievances. Is it working?
I think it's working. I talk.
Nah,
locking
wait.
for your slides.
It's wait. Yeah. Okay.
Yeah, it's working.
Yeah. Good job.
Alright, good job.
Alright. Now I need just.
Yeah, test if the stream's working. Is it audio?
Yeah.
Yeah, you can play around.
Okay, that's.
I don't know how to add a page though, so I'm not just like.
Oh, true. Yo. Wait, we can't do that, right?
I don't know how to use this laptop.
Sometimes. Wait, you good now?
Yeah, I think we're good.
Okay, add a page.
I think he can like tell you when you're like when I'm presenting, like teach you.
No, like you can't add a page on like.
Oh, you just can't.
I don't know. You just have to run on the side. Oh, okay.
Yeah.
I have to run on the side. Yeah, just you have to count as the side space. Wait, that means we can't use black for the side. No, I just use red. I used red at that time. Yeah. Okay.
Oh, you can run on the side. What the?
Yeah. It's just like a full like blank canvas.
Yeah. Okay, that's good. That's
okay.
Good. That's good.
Guys, this stack's cool. Not gonna lie, I thought it was cooked at the start, but then like at the end I was like, yeah, it's not too bad. Like final's easy for mine. I don't know, maybe it's too easy for my ears, and maybe like it's gonna cook it up for you guys. So I might just be.
Okay.
I hear it if he's watching this.
Let's get started then. So I'll be doing the first 3 chapters, and Zayden will be doing the last 2 chapters. Zayden's over there. So intro to probability, we'll start with that. So I'm sure you've seen all these definitions before. I'm not going to go into too much detail. Basic definitions. An outcome. Wait, can you guys hear me by the way? Because we don't have a mic. Okay, that's all good. An outcome is a possible result of an experiment. A basic example would just be flipping heads on a coin. Sample space is a set of all possible outcomes of the experiment. An event is a set of outcomes with an assigned probability. So anything that's like feasible to happen. No audio.
We'll fix something.
What happened?
No, it's fine. It's just like we delete this and then re-add it. No, it's a stupid issue that always happens every time. Yeah, it should work.
Okay, it should work. Probability functions. A probability function, which is this capital P here, is a function that returns the probability of an event. It must satisfy these properties. These are probably fairly intuitive. All properties must lie between 0 and 1, inclusive. The probability of the sample space is 1, and the probability of any event and its complement add up to 1. So the first law we have is the inclusion-exclusion, or you could think of it as an additive law. So for any 2 events, A and B, the probability of their union is just the probability of A plus the probability of B minus the probability of their intersection. If A and B are mutually exclusive, then the probability of the intersection is simply 0 over here. So now we can move on to conditional probability. So the conditional probability of A given B, so the notation looks like this. We have A and we have given something else, is the probability of A intersection B divided by the probability of B. We need the probability of B to be non-zero. So then this gives us our multiplicative law, which is basically just when we rearrange this here. So our probability of A intersection B is the probability of A given B times the probability of B. And for 3 events, we can extend the formula to this over here. So if we were to expand the right-hand side here, using what we have up here, you'll see that everything simplifies to the left-hand side. Basic probability results. So let P be a probability function on the sample space S, then the following hold. The probability of the empty set, which is nothing, is 0. That should make sense. The complement rule, which is the probability of the complement of an event, is 1 minus the probability of the event. Monotonicity is if A is a subset of B, which is the subset of the sample space, then our probability of A is less than or equal to probability of B. We also have the union bound, which is the probability of A union B is less than or equal to the probability of A plus the probability of B. So this comes from this result here, would come from here, where we just get rid of this one here to get an inequality. Inclusion, exclusion, I already mentioned that. So independence. So 2 events are independent if and only if the probability of A intersection B is the probability of B times the probability of A. I read that the wrong other way around, but that's fine. So using conditional probability, this is equivalent to having probability of A given B is equal to the probability A. So you can interpret this as the probability of A given that B happened is still just the probability of A. So it kind of makes sense why you call this independence. So if we have a set of events, the set of events are called pairwise independent if the probability of AI intersection AJ is just the probability of AI times the probability of AJ for all I that is not equal to J. Now we have a stronger condition which is called mutually independent. So a set of events is mutually independent if we can I guess, factor out this thing into all the products of the individual events. So mutual independence implies pairwise independence, but pairwise independence does not imply mutual independence. So mutual independence is a strictly stronger condition. So the law of total probability. So if we have two events A and B, do you agree that A and A complement form wait, what am I up to? Yeah. So for two events A and B, we have the probability of B is equal to the probability of B intersection A plus the probability of B intersection A complement. This is because A and A complement form a partition of the sample space. So then we can express B as B intersection A, and then union this with B intersection A complement. Now, if we apply the probability function to both sides, we can get the probability of B is equal to the probability of B intersection A union B intersection A complement. Now, since this event and this event, they're mutually exclusive, so we can just break apart the probabilities and we get what we need. And equivalently, we can use conditional probabilities to expand each of these intersections to get what we need over here. So this is pretty useful. But yeah, so this is the general version where instead of just having two events partitioning the sample space, we have A1 all the way to AN partitions the sample space. So it's basically the same thing. The probability of B is the sum of the probabilities of B intersection AI. So it comes from something similar to what we have up here. And of course, you can use conditional probabilities to break it up. So complements in conditional spaces. Now, if A and B are events, then we have the probability of A complement given B is 1 minus the probability of A given B. Okay, so this comes from the probability of I think this cable's a bit short. So this comes from the probability of B is equal to the, what am I up to? Probability of B intersection A plus probability of B intersection A complement. And if we were to divide both sides by probability of B, we get 1 equals the probability of B intersection A divided by probability. Probability of B plus probability of B intersection A complement divided by probability of B. Now, if you recognize this part is just probability of A given B, and this part is probability of A complement given B. And if we rearrange this, we get our result that we need up here. Yeah, that's just the typed off proof. Now, Bayes' law. So if we have A and B are events with the probability of B non-zero, then we can essentially flip around the order of the conditional probabilities. So we can get the probability of A given B is the probability of B given A, but we have to correct it by this one over here. So don't forget that. So if we start from the left-hand side, the probability of A given B, that's just, if you recall, the probability of A intersection B divided by the probability of B. And what we can do is so A intersection B is the same thing as B intersection A. We can multiply by probability of A, and probability of B here. So I've just multiplied by probability A and probability of A. And this term over here is just probability of B given A, and we have our probability of A divided by probability of B. So that's where this comes from. So this is very useful because sometimes the probability of A given B is difficult to understand and compute, but probability of B given A might make more sense to you. It might be simpler to compute. So keep in mind that you can almost flip them around. You just need to include this term here. So this is the more general version. If A1 all the way to AN partition the sample space and B is an event, then we have the probability of AJ given B is equal to this over here. So this is basically what we had up here. And we can also replace probability of B, if you remember our total probability rule, with this sum over here. Okay, we have a question. So MathSoc is trying to catch people who secretly claim they have proved the Riemann hypothesis. Every society member is either a fraud or legitimate. Historically, 8% of members are frauds. To identify frauds, 2 independent judges are employed. Math fraud correctly identifies frauds 90% of the time and correctly identifies legitimate members 95% of the time. Math monkey correctly identifies frauds 85% of the time and correctly identifies legitimate members 92% of the time. If a randomly selected member is approved by both math fraud and math monkey, what is the probability that they are actually a fraud? So I think this is a pretty classical question. I'm pretty sure there was like a version of this in test 1. So yeah. So let A be the event that math fraud says the person is a fraud, and B be the event that math monkey says the person is a fraud. And let F, for fraud, be the event that the person is actually a fraud. Then we have the probability of A. So probability that math fraud says the person is a fraud, given that they're actually a fraud, is 0.9, which comes from this 90% up here. And the probability that math fraud says they're not a fraud, given that they're actually not a fraud, is 0.95, which is what we have up here. And likewise, we have these two from Math Monkey. Note that we have the probability of fraud is 0.08, because historically 8% of members are frauds. We also have probability of math fraud saying they're a fraud, given that they're not a fraud, is 0.95. That comes from here, where we use the complements. So 1 minus 0.95 equals 0.05, which is what we have here. And same thing for this one over here. So we're looking for the probability that someone is a fraud, given that they were approved by both math fraud and math monkey, which, if you convert it into what we defined up here, becomes the probability of fraud given that they're approved by both judges. Now, this is a bit hard to comprehend what that really means. And if you try like flipping it around using our Bayes law, the probability of this one here is a bit easier to comprehend. But remember, we have to account for, we can't just flip it around, we also have to account for this factor over here. So this part here is the probability that they're a fraud, and this long part down here is just the probability of this event here. So you see how we have F, and we say F complement. So this forms a partition, which is why we can break it up into this sum over here. So a common mistake is saying that the probability of A complement intersection B complement is the probability of A complement intersection the probability. I think this should be a times. Yes, probability of B complement. So this incorrectly assumes that if math fraud says the person is legit, then it's independent from what math monkey would also say the person is legit. the judges are only independent given the actual nature of the person. So then we have the probability of A complement intersection B complement, given that they're a fraud. We would have to break it up like this, which, if you recall from up here, we have our numbers is 0.1 and 0.15. I don't use this. And we also have this term down here. And if you sub in all your numbers, sub everything back up into here, we get 0.00149. So some notes about this question. So is probability of A given F 0.9, or is it probability of F given A is at 0.9? So the correct answer is we actually have the probability of, I believe it was math fraud, saying it was a fraud, given that the actually fraud is 0.9. It's not the other way around, because the other way around represents a different context. Because I think if you look up here, the judges identify based on what the members actually are. This is their accuracy, basically. And a note about independence, which is part of the trick, I guess, that this question holds. We assume that the two judges' decisions are independent, given the true status of the person. So once we know whether someone is actually a fraud or not, knowing what one judge says gives no additional information about what the other judge says. Okay, guess we can go to random variables. So a random variable is a function that goes from the sample space to the reals, which assigns a numerical value to each outcome of a random experiment. So you can think of it informally as a rule that turns outcomes of a random experiment into numbers, probabilities. So a side note, events like the random variable x is less than or equal to little x, or x equals k, they're really shorthands for subsets of the sample space. So this is really a shorthand for this, and this is really a shorthand for this. And since these are events, we can assign them probabilities using our probability function. The distribution. So distribution of the random variable x is the collection of probabilities of x within this measurable set B. So it's basically just the rule that assigns probabilities to values or ranges of values of x. The CDF, the cumulative distribution function of a random variable x, is simply just the probability that the random variable x is less than or equal to little x. Now, there are some common tricks we can use with CDFs. The main one of them being the probability that x, random variable x, is greater than little x is 1 minus the probability that 1 minus the CDF evaluated at x. And for any x less than y, we have the probability of x between x and y is just the CDF at y minus the CDF at x. Here's some properties of CDFs. Okay. So suppose f is a CDF, then the following apply. The CDF will be between 0 and 1, and the limit as x approaches negative infinity of the CDF should be 0. And the limit as x approaches positive infinity of the CDF should be 1. And f is also non-decreasing for all x, just means this. And this one I've already covered. The probability that x is greater than x is 1 minus the CDF at x. This one I've also covered. And f is right continuous, which satisfies this condition here. So it's not, yeah. So support / domain of variation. I think we use domain of variation more, but I think support was in the exam for some reason. So the support or domain of variation of a discrete random variable, denoted as x, is a set of all values of x with positive, so it has to be positive non-zero probability. So basically, these are the values that x can take. So for example, if x we define as the number of heads we get when flipping 3 coins, the support will be 0, 1, 2, or 3. So it's because we can get 0, 1, 2, or 3 heads when flipping 3 coins. So the reason some number like 4, the reason a number like 4 isn't in our domain of variation is you can't get 4 heads from flipping 3 coins. So you could say the probability of that is 0, so we won't include that in our domain of variation. Discrete random variables. So a random variable is discrete if it can take a countable number of values. So that just means we can list it in a finite or infinite sequence. Probability mass function. The probability mass function of a discrete random variable x is just defined using this little p of our random variable x. It's just the probability that our random variable is equal to x. Now we can get the CDF of our discrete random variable as it's just the sum of all the PMFs taking values less than or equal to k. Less than or equal to x. And here are some properties of the PMFs. So as usual, the probabilities are between 0 and 1. Our probability is sum to 1. Our CDF is defined like this. And if we want to make the PMF the subject, we can have the PMF of x is equal to the CDF of x minus the CDF of the value right before x. So a random variable is continuous if it can take a continuum of values. So a probability density function written like fx, so little fx, of a continuous random variable x is a positive function that satisfies this. It's not very rigorous, but it should be fine. And likewise, the domain of variation for continuous random variable x, denoted as Sx, is the set of all values of x where the PDF is positive. So once again, it's that greater than 0 condition. And as usual, we have properties of PDFs. We can get our CDF of a continuous random variable by integrating from -infinity to x of our PDF. We can also get it back by differentiating the CDF. And of course, we have the probabilities are greater than or equal to 0, and that all the probabilities added together is 1. So move on to expectations. So the expectation of a random variable is its mean or average. So for a discrete random variable with support Sx, it's simply defined as the sum of x times the probability of x across all values of x in our domain of variation. And for continuous random variables, it's basically the same thing, but we have the integral from -infinity to infinity of x times our PDF. So we can use the symbol mu interchangeably with expectation of x. They're the same. Now, expectations of functions of random variables. So if we have a function g from R to R, our expectation of g of x, quite conveniently, all we have to do is replace x with g of x here. And as usual, it's across all x in a domain of variation. So properties of expectations. Let a and b be real constants and x and y be random variables. The expectation of a constant is a constant. Expectations are linear, so if we have the expectation of ax plus b, it can become the a times the expectation of x plus b. And we also have this result here, which hold in general. So additionally, if x and y are independent, then we can break this expectation of xy into the expectation of x times the expectation of y. So this one requires independence, this one does not. So this one's more general. So some more definitions. Moments. So the kth moment of a continuous random variable is just defined as the expectation of x to the power of k. And if you recall from expectations of functions of random variables, this is just, we replace x with x to the k here. We also have central moments, which is just, you have x minus mu to the power of k instead of just x to the k. And as usual, we just replace the function. We just insert the function here. So this is for continuous random variables. For discrete random variables, they're defined similarly, but we have sums instead of integrals. Variance. So the variance of a random variable x is a measure of its spread from its mean. It's defined as the expectation of x minus the mean squared. You could also use an alternative form, which is expectation of x squared minus the expectation of x entire thing squared. And of course, standard deviation is the square root of the variance, and it's denoted by sigma. We have some properties of variances. A variance is always greater than or equal to 0, so it's non-negative. Variance, however, is not exactly linear. We have the variance of ax plus b is a squared times the variance of x. So this constant kind of disappears, and this a becomes a squared if you pull it out. So we have a simple question over here. Suppose x is a continuous random variable with PDF defined like this. It's like this and 0 otherwise. Find k such that the above function is a PDF function. Part 2 is compute the expected value, and part 3 is compute the variance of x. Yeah. So if we recall, for a continuous random variable with PDF like this, we need to have the integral from negative infinity to infinity of our PDF. It's going to equal 1. But in this case, since it's 0 outside of this interval over here, we could just become, it becomes this. So if you also evaluate this integral over here, you'll get some number, and then k would just be 1 divided by this number over here. So hopefully we all know how to integrate this. We've got the dx. So compute the expected value of x. So if you remember the expected value of x, 2 given by the integral, we have x times of our PDF. And then whatever we got for k, which apparently is 1/18 if you were to solve this integral, we would just have to integrate this. And then this would give us our expected value. Now for part 3, which is compute the variance. So the variance of x, we will use this form over here because it's usually easier to deal with, straight up at least, is the expectation of x squared minus the expectation of x times x squared. Now we already have this over here from part 2. We just need to calculate the expectation of x squared. Now the expectation of x squared, it's an expectation of a function of x. So if you recall, it's just we replace the function, becomes x squared inside here. Like this. And you'll find a value for the expectation of x squared. And you just have to sub it in here. And if you do it correctly, you'll get these values here. Now here's another question about manipulating expected values. So let x and y be random variables with finite variance. Show that for any real t, the expectation of tx plus y whole thing squared, or the inside squared, is greater than or equal to 0, and deduce that the quadratic in t is given by this and has at most 1 root. So for something like this, it's a square, so it's always greater than or equal to 0. And if you remember our expectation, you can think of it as an average. And since these values are always greater than or equal to 0, the expectation would have to be greater than or equal to 0. Now we need to deduce this has at most one real root. So if we expand this over here, we get expectation of t squared x squared plus 2txy plus y squared. Now since we can use linearity to simplify this more, becomes expectation of t squared x squared plus expectation of 2txy plus expectation of y squared. Now we can also pull the constants out, so t squared expectation of x squared plus 2t expectation of xy plus expectation of y squared, which is what we have, which is our expression over here. Now this has at most one root because it's greater than or equal to 0. So hence prove the Cauchy-Schwarz inequality. So we have t squared expectation of x squared is 2t expectation of xy so this is a quadratic in t with at most one real root. Now that means our discriminant have to be less than or equal to 0. If you take our discriminant, which is, hopefully you remember, b squared minus 4ac, we have 2t expectation of xy. T, how do I log out? 2 expectation of xy squared minus 4 expectation of x squared is less than or equal to 0. See, if you rearrange this, we'll get our required result here. So moment generating functions, MGFs. So let x be a random variable. We define the moment generating function of x as this x and s, which is just the expectation of e to the power of sx. So we have some properties of the MGF, which is that the MGF of ax is just the MGF of x, but you evaluate it at a times s for any constant a. We also have the MGF of x plus b, so shifted by a constant, is just e to the power of bs times the MGF of x. We also have, which is I guess the most important property, is that the derivatives of the MGF gives us our moments, which if you recall were just the expectations of powers of x. So the kth derivative of our MGF will give us the kth moment, which is why it's called a moment generating function probably, because it generates our moments. So if you look at property 1, the proof is here. Our MGF of ax, s, is just the expectation of s times ax, because that's how we defined our MGF here. And that is, we can move the brackets around, the expectation of e to the power of as times x, and then it just becomes this. Pretty similar for the second property. We just use exponential laws. We take the e to the bs out because it's a constant, and we can just, it's not a constant, but we can like take it out. There's no random variable there, so we can factor out here. And property 3 just shows you how we can generate our moments by differentiating our MGF. So if we differentiate with respect to s, hopefully you remember how to differentiate e to the sx. That's just, we bring the derivative of the exponent to the front, which is just x in this case. So if you do that k times, you'll get x to the k. And taking s approaches 0 gives us the expectation of x to the power of k. So why do we care about MGFs? So MGFs are useful for two main things. One is finding the moments of a distribution, so which is x to the power k. You just have to take the kth derivative. The second one is identifying distributions. So MGFs are unique to a distribution. So if you wanted to prove that x follows a given distribution, one way is to find the MGF of x and write it in the form of the MGF of a known distribution. This could be easier than actually finding the PDF, PMF, or CDF. So standardization. So let's say we have a random variable x with mean e to the x, mu, and variance sigma squared. Then the standardized version, which is given by this asterisk over here, is x minus the mean divided by the standard deviation. Now this is called standardization because when we take the expectation of it, we have expectation is 0 and the variance is 1. So it's like neat numbers. So a quick proof, the expectation of x asterisk, which is our standardized one, is the expectation of this over here. And since expectations are linear, we can take out the 1 on sigma and factor it like this. And since these are equal, they cancel to equal 0. And something similar for the variance as well. But keep in mind that we have to square the constant when we pull it out. So it becomes 1 on sigma squared over here. And it gives you 1 in the end. Useful inequalities. I recommend just put these on your formula sheet so that you don't forget about them on your exam. But we have Markov's inequality, which is if x is a non-negative random variable and a is positive, then we have the probability that x is greater or equal to a is less than or equal to expectation of x divided by a. So it's bounded from above by this over here. So we also have Chebyshev's inequality. Let x be any random variable with mean mu and variance sigma squared. Then for any k greater than 0, the probability that x is more than k sigma away from the mean, which is, I guess, an interpretation of this, is also bounded by 1 on k squared. So we have a bounding problem here. So a factory produces 600 machines a day on average. It is subject to a variance of 100. Let x be the amount of machines produced tomorrow. Find a lower bound, so a lower bound for the probability that between 500 to 700 machines are produced tomorrow. So in other words, we want a bound for this probability here. So the probability that between 500 and 700 machines are produced tomorrow. So if we write it in this form, which is the absolute value of x minus 600 is less than 100, we can use Chebyshev's inequality, which is over here. We have to change the direction of this inequality first. Becomes 1 minus the probability of this is greater than or equal to 100. So since we have a mean of 600 and a standard deviation of 10, we have that the probability that x minus 600 is greater than or equal to 100 is bounded by 1 on 10 squared. So this 100 is just 10 sigma. And this 10 is our k over here, which is why we have 1 on k squared, which is how we have 1 on 100. So then if we sub it back in here, we get 1 minus 1 on 100, which is 99 over 100. Jensen's inequality. So here's a definition for a convex function. I kind of doubt we'll ever explicitly use this. But if h is twice differentiable, this is equivalent to saying the double diff is greater than or equal to 0 for all x in the domain. So Jensen's inequality says if x is a random variable and h is a convex function, so it satisfies this up here, then we have the h of the expectation is less than or equal to expectation of h of x. So an example of a convex function is x squared. So then we would have expectation of x squared. So we're applying x squared to expectation of x. It will be less than or equal to expectation of x squared. Now, if you remember, this is actually our variance. So then this proves that our variance is non-negative. So, yeah. So another way we can use Jensen's is if we have like a concave function. So it's like the other way around. If we have a concave function instead, I believe this inequality would just flip around. It would be greater than or equal to for a concave function. Mode and median. Mode of a continuous random variable is a value x in our domain of variation such that f of x at x is greater than or equal to f of x at y for all other values of y in our domain of variation. So the mode of a continuous random variable is just a global maximum of the PDF. The mode of a discrete random variable is basically the same, but like you define it accordingly, global maximum of the PMF. The median of a random variable denoted Q 0.5, so Q for quantile, 0.5 for our quantile level, is as small as x such that, I think this should be the other way around. The probability that x is less than or equal to x, which is our CDF, is greater than half, greater than or equal to half. Yeah, quantiles. So the quantile level of alpha of a random variable, which is denoted Q alpha. So up here we had Q 0.5. So the median is the quantile level half. Q alpha is the smallest x such that our CDF at x is greater than or equal to alpha. That is, it satisfies this. We also have the quantile function, which goes from 0 to 1 to reals and is given by this. So basically outputs our quantile level of alpha. So let's move on to random vectors. Joint CDF. Okay. So the joint CDF of a bivariate random vector. So it's just the random vector has got two components in it. It's got x1 and x2, which are each individual random variables. It is a function f x1, x2. So to show that we have both x1, x2, we just write them as subscripts down here. And it goes from R2 to 0 to 1 because we're outputting a probability which is between 0 and 1. And it's defined like this. So the CDF of x1, x2 at x1, x2 is just the probability that x1 is less than x1 intersection x2 less than x2. So normally you'll see it written like this instead of this form. So we're basically just replacing our intersection with a comma. It's just a shorthand, it's more convenient, but just know that they mean the same thing. Now we also have some properties of our joint CDFs. So just like our univariate CDF, the limit as we take both x1 and x2 to infinity is just 1. So it's similar to our previous cases. And here, if we fix x2, I think Tom's pen died. So if we fix x2 and we take x1 to negative infinity, our CDF approaches 0, and same thing here for the other case. Zeta, can you call Tom? I think his pen died. And here, if we fix x2 in 0.3, and we take, if we fix x1, and we take x2 to infinity, we essentially remove the other variable x2 and we obtain the marginal CDF of x1. And it's the same thing for the other case here. Scroll. Here we go. So here's some reasoning behind these results. So if we take the limit of x1, x2 to infinity of our CDF, it's essentially the probability that both these random variables are less than or equal to infinity, which is of course is equal to 1. If we take the limit of x1 as it approaches negative, sorry, the limit of the CDF as x1 approaches negative infinity, we have the probability that x1 is less than or equal to negative infinity, and we hold x2 less than or equal to x2. That's equal to 0. Yeah. So joint PMF. So that was the joint CDF. We have the joint PMF as well. So the joint PMF probability mass function of a discrete bivariate random vector x, which is x1, x2, is the function little p of x1, x2 that goes from R2 to 0 to 1 because we're outputting a probability. And it's given by just the probability of x1 equals x1 intersection probability x2 equals x2. So we have some properties here. The CDF of our discrete case is just the double sum of our PMF. So if you imagine this, I can't really draw right now. If you imagine this, we have the sum from x1 is less than or x1 dash is less than or equal to x1, and we have the sum of x2 dash is less than or equal to x2. And down here, we can also recover the individual PMFs. So if we wanted to do the PMF of x1, we would have to sum across the joint PMF. We have to sum across all values of x2 in our domain of variation for x2. And similar for x2, if we want the individual PMFs of x2, we will have to sum over all values of x1. Joint PDF. So a bivariate random variable x, with both components being continuous random variables, is said to be continuous if there exists little f of x1, x2, which goes from R2 to R, that satisfies this condition over here for any subset of R2. So this function is called the joint PDF of x. So once again, we have some properties. They're just extensions of what we saw in like the univariate case. The PDF of x1, x2 is greater than or equal to 0. And we have that the total sum of all the probabilities is equal to 1 in our second case here. And we have the CDF is just defined as the double integral from negative infinity to x1 and negative infinity to x2 of our PDF. So properties of joint PDFs. Number 4 is if our joint CDF is differentiable, then we can obtain our joint PDF by simply taking the partial derivative of our CDF with respect to the variables. And point 5 says that we can recover the individual, or we could say marginal PDFs. So for example, the marginal PDF of x1 is equal to, if we integrate the joint PDF, if we integrate over x2. So if we want the marginal of x1, we integrate over x2. And for any subset A of R2, we have the probability that x1, x2 is in A is simply the double integral over our area A of our joint PDF. So we have some fairly important stuff which talks about independence in terms of joint distributions. So x1, x2 be random variables, then x1 and x2 are said to be independent if and only if we can factorize our CDF into the individual marginal CDFs. So in particular, if x1, x2 are discrete, then they are independent if and only if we can factorize our joint PMF into the individual marginal PMFs. And likewise, if x1, x2 are continuous, they're independent if and only if we can factorize our PDF into the individual PDFs. marginal PDFs. So I'm sure you know, but we write this symbol to show that they are independent. And I think this slide is just a summary of what we did on the previous slide. So it's just saying independent if only if we can factorize the CDF or PMF or PDF. So if we consider using conditional PDFs, two continuous random variables x1, x2 are independent if only if the conditional PDF of x1 given x2 is equal to the marginal PDF of x1. Or we could have it the other way around. The conditional PDF of x2 given x1 is equal to the marginal PDF of x2. So likewise to our univariate case, it's like we're just ignoring, it's kind of like we're just ignoring this part over here. And we're just obtaining this. Oops. Yeah, it's kind of like we're just ignoring this. That shows independence. And likewise in the discrete case where we're just using PMFs instead of PDFs. So conditional PMF. So if x1, x2 are discrete random variables, the conditional PMF of x2 given x1 is defined for any fixed sx1 by the conditional PMF of x2 given x1 is just the joint PMF divided by the marginal PMF of our conditioning variable. So this is our joint PMF, and this is the PMF of our conditioning variable. So it's like whatever's on the other side here. And likewise for the conditional PDF, except we're just using PDFs instead of PMFs, basically. So bivariate question. So let x and y be random variables with the joint density function given by this expression here. Part I, determine the marginal density of Fy of y. Part 2, determine the conditional density. Part 3, are they independent? And part 4, calculate this probability here. So what is the marginal density? Well, I've mentioned a few times, but the marginal density function is obtained by integrating out the other variable that you don't want from the joint density function. So if we wanted the marginal density of x, then we would have to integrate the joint density over y. So we're integrating out the other variable from the joint density function. Likewise for discrete, but we're summing over the variable that we want to get rid of. So in part I, to determine the marginal density of y, we would have to integrate over the joint density with respect to x. So which is what we have over here. The marginal density of y is we're integrating the joint density over x. And the joint density was just expression here, and we're integrating over x. I'm sure we know how to integrate an exponential, so we end up with this, which is the marginal density of y. Part 2, determine the conditional density. So if you recall, the conditional density of y given x would just be the joint density of x and y divided by the marginal density of x. So similarly, we can obtain our marginal density for x by integrating over y. And from our formula, we can see that this is our joint density, which is this one here, and we're just dividing by the marginal density of x, which you get over here. Now, part 3, are they independent? So remember, they're independent if and only if we can factor the PDF. So from part I, we know that the marginal density of y is this expression here. And from part 2, we know that our conditional density is this, Therefore, they're independent, as the conditional density of y given x is just equal to the conditional density of y. So that's another way we can tell independence, can determine independence. If our conditional is equal to our marginal. So we need to calculate the probability that x plus y is less than 1. So to do that, we can find the probability of a joint density function by integrating over a given area. This condition here, x plus y is less than 1, corresponds to the condition x plus y is less than 1. So that's the area of R2 that we're interested in. So if we integrate using a double integral from MATH2801, our joint PDF using these bounds over here. So to get those bounds, we just have something like this. It's just this area in here where this is 1 and this is 1. So we're integrating x from 0 to 1, and when we fix x, we're integrating y from 0 to 1 minus x. So that's how we do it. And if you evaluate that, we get this expression, we get this probability over here. Which diagram? This diagram? Yeah, okay, sure. So yeah, I don't have a pen, so I can't really draw it properly. But so this axis down here is the x-axis, right? And this one up here is the y-axis. And to satisfy this condition, we just want to integrate over this area here. So this line here is y equals 1 minus x. Okay. And this value up here is 1, and this value down here is 1 as well, right? And do you remember how to do double integrals from MATH2801 or? Yeah. So if we do the order of dy dx, if we integrate, so we fix x goes between 0 and 1, and y goes between 0 and 1 minus x. Does that make a bit more sense? So then that's how we get these bounds over here. Is that right? Or okay. So then once we have these bounds, we just do some integration and we get this probability here. So conditional expectations and variances. So the conditional expectation of g of x given y equals y. So a conditional expectation of this given this. In the discrete case, it's just the sum over all x of g of x times the conditional PMF. So it makes sense because our original expectation of x is just the sum of x times the PMF of x, right? Here, when we have a function, we just replace x with the function. And we also replace, and since we also have a condition, we're just replacing the marginal PMF with a conditional PMF over here. And in the continuous case, it's the same, but we have an integral over all the real. So if y is not given, so if this y is not given, then essentially this, what's inside here becomes a random variable on y. So conditional variances, once again, we have our normal variance is variance of x equals expectation of x squared minus expectation of everything squared. But when we introduce a condition, we simply basically just append it on here. We append it in here, here, and here. So you see, if we cover this, we get our univariate variance for x. But to get our conditional variance of x given y, we just have to put it in there. So it should be fairly not too bad to remember. So law of total expectation. I don't think our lecturer explicitly covered this, but it was in the midterm, and It was in some tutorial questions, so it's probably worth it. So if x and y are random variables, then the expectation of x is the expectation of x given y. So remember that this thing inside here is a random variable because we're not given y. So because y is arbitrary, sorry. So we can express the expectation of x given y as g of y. So then we have g of y is expectation of x given y equals y. So to use the law of total expectation to calculate by computing this, these are the steps to follow. So firstly, you want to find the expectation of x given y equals y for an arbitrary y. Then whatever expression you get for y, you have the expectation of x given y is just the function applied to y. And now you just have to simply calculate expectation of g of y. So that's probably a bit confusing, so let's go through an example. So the number of cores, n, so n is the number of cores, arriving at a core center in an hour follows a Poisson distribution with the rate capital lambda, where capital lambda itself varies hour from hour and is uniformly distributed on 2 to 10. So capital lambda follows uniform distribution, and the number of cores follows a Poisson distribution with rate capital lambda. So we can summarize this like this, and we have the number of cores given that capital lambda is equal to lambda follows this distribution here. The part I is find the expectation of n, so the expectation of the number of cores, using the total law of total expectation. So since this random variable here is distributed like this, we know that expectation of this random variable is just lambda. So that's a property of the Poisson distribution that Zayden will do. And we have the expectation of n given capital lambda is capital lambda. By the law of total expectations, the expectation of n is the expectation of n given capital lambda. And if you recall from up here, we have the expectation of n given lambda is just lambda. So then this simplifies to expectation of lambda. And since lambda is uniformly distributed from 2 to 10, the expectation is just this over here. Like the average, 2 plus 10 divided by 2. So the balance divided by 2, which gives you 6, which is how we get the expectation of n is equal to 6. So part 2 is, suppose each core is independently a complaint with probability 0.1. Let C denote the number of complaints in the hour and find the expectation of C by conditioning on n. So it's basically telling us to use the law of iterated expectation. So find expectation of C by conditioning on n, which is basically what we have over here. So given that we have n cores and that each core is independently a complaint with probability 0.1, we have that the number of complaints, given that we get n cores, is binomially distributed like this. And if you recall the expectation of a binomial distribution, it's just these two parameters multiplied together, which is why the expectation of this random variable here is 0.1n. Now, if we replace this little n with capital N for arbitrary n, we get that the expectation of c given n is just 0.1 n. And by the law of total expectation, the expectation of c, which is expectation of the expectation of c given n, which from here is just 0.1 n, so it becomes the expectation of 0.1 n. And since expectations are linear, we can pull out the 0.1, and it becomes 0.1 times the expectation of n, which is just 0.1 times 6, which from part 1, expectation of n is just 6. So expectation of c is just 0.1 times 6, which is 0.6. So expectations of functions of random variables. So if x and y are random variables, then the expectation of a function g of x and y, once again, we just replace whatever is here with g of x and y. And since we're in a bivariate case, we have to sum over both of them. Sum over both their domains of variations. In the discrete case, so that's in the discrete case, and in the continuous case, we just replace it with integrals. So if x and y are independent random variables, then for any functions h1 and h2, we have that the expectation of h1 times h2 of y is, we can split it up into the expectation of h1 of x and the expectation of h2 of y. So this requires independence. So we have a bivariate discrete question. So we're given this table over here. You can see that the domain of variation of x is here. For y, it's over here. Part I, determine the marginal distribution of x. Part 2, are x and y independent? And part 3, what is the covariance between x and y? So if you remember, for part I, to determine the marginal distribution of x, we would have to, in the discrete case, sum over the values of y. So if we hold x at 0, then for the probability of x equals 0, we would have to sum over y, which is what we get from 0.15 plus 0.12 plus 0.06, which gives us our 0.33. And same thing for x equals 1. We just have to sum over the y's. So we get 0.9, 0.09, 0.12, and 0.09 here. And same thing for x equals 2. So this is our marginal distribution of x. So part 2, are x and y independent? Give reasons. So we can see that f of y at 0, which if you recall, to get the marginal density of y, we have to sum over x, is 0.15 plus 0.09 plus 0.06, which comes from summing this ways and gives us 0.3. And from the table, we can see that the PMF at 0, 0, which is over here, is 0.15. But that is not equal to that is not equal to the marginal of x at 0 and the marginal of y at 0. And since we cannot factorize it like that, they're not independent. Part 3, what is the covariance between x and y? So definition of covariance. So the covariance of two random variables, x and y, is a measure of their joint variability and is given by this over here. So it's the expectation of x minus mu x and y minus mu y. Alternatively, you probably use this form a bit more. It's the expectation of xy minus the expectation of x times the expectation of y. So some properties they should probably remember. if x and y are independent, then we have the covariance of x and y are 0. However, it doesn't go the other way around. We also have the covariance of xy is equal to the covariance of yx. And we also have that for any reals a and b, we can break up the covariance like this. Variance of a linear combination. So if x and y are random variables, then the variance of ax plus by is a squared variance of x plus b squared variance of y. We also need to include this this covariance term over here. So the special case you'll probably use more often is simply just when you're adding or subtracting two random variables and you want the variance between them. So in that case, it's just variance of x plus variance of y plus minus 2 times the covariance. Now recall that if x1 and xn are x1 all the way to xn are independent, then their covariances are 0. So then in the independent case, we can just break up the variances and we don't need to worry about covariances. That's only if they're independent. Covariances in terms of variances, I don't know how useful this is, but I guess sometimes it's easier to find the variance of x plus y than using this term over here. So let's go back to part 3. What is the covariance between x and y? So if you remember the covariance, is expectation of x, y. And then we also have, so if you remember, the covariance is expectation of xy minus the expectation of x times the expectation of y. So we just need to calculate this to find the covariance. So we have our marginal PMFs here. And using that, we can calculate our expectations individually. So it's just 0.3 times 0. So what we get from here, 0.3 times 1, and then 0.37 times 2. That's how we get the expectation of x. Expectation of y, however, is the same thing. We just have 0.3 times 0, 0.4 times 1, and 0.3 times 2. And that gives us an expectation of 1. So now all we have to do is find the expectation of xy. So to find the expectation of xy, for a discrete case, remember we can just go like this. Something like that. So if you look at all the possible combinations of x and y, we're going to obtain 0, 1, 2, or 4. To get xy equals 0, we simply have these cases. So we just have to add all these probabilities up. So 0.15 plus 0.12 plus 0.06, 0.09, and 0.06 to get the probability at 0.48. And when xy equals 1, so the only case where xy can equal 1 is when you have 1 times 1. So the probability of that is just 0.12. And xy equals 2, the only two cases is when you have 1 and 2 and 1 and 2. So if you add these two probabilities up, we get 0.25. And likewise, the only case where we can get xy equals 4 is when we have 2 times 2, which is what happens over here. So 2 times 2, so 0.15. So therefore, we can get the expectation of xy as 0 times 0.48 plus 0.12 times 1 plus 0.25 times 2 plus 0.15 times 4, which we end up with 1.22. Hence, we get the covariance to be 1.22 minus this, which we end up with 0.18. Correlation. So correlation is a measure of the strength of the linear relationship between two random variables, and is given by this expression here. So correlation of 1 and 2 of the random variables 1 and 2 is the covariance of x and y divided by the square root of the product of their variances. So the correlation would always be a value between -1 and 1. A value of 1 indicates a perfect positive linear relationship, while a value of -1 indicates a perfect negative linear relationship. So x and y are said to be uncorrelated if our correlation coefficient is 0. Now we have the weak law of large numbers. So we have some setup. So let x1, x2 be a random sample of independent and identically distributed random variables with expectation of xi mu and variance that's finite. And define our sample mean to be 1 divided by the sum of our xi's. So the weak law of large numbers says that as n approaches infinity, so as our sample gets bigger, our sample mean converges to mu in probability. So we can express that like this, with an arrow with a p on top of it. So this p means convergence in probability. And what does that mean? It means that for all epsilon greater than 0, our probability that our sample mean, the absolute value of our sample mean minus our mu greater than epsilon approaches 0 as n approaches infinity. So I think there's like an alternative way of this, where we can write our sample mean minus mu is less than epsilon approaches 1 as n approaches infinity. So these two are equivalent. It might be easier to use one of them in some cases, but yeah. We also have the strong law of large numbers. Under the same assumptions over here, we have that the sample mean converges to mu almost surely. So up here, it was convergence in probability for weak law, and for the strong law, it's convergence to mu almost surely. Now we can denote this using an arrow with a.s on top of the arrow for almost surely. And this just means that the probability of the limit as n approaches infinity of the sample mean equaling mu is just 1. So what's the difference between weak and strong? For the weak law of large numbers, for each fixed large n, the sample mean is likely to be close to mu, but the sequence may still stray far from mu infinitely often. It's just that there's vanishing probability at each step. For the strong law of large numbers, however, the entire path converges to mu with probability 1. So almost every realized sequence of xn's settles down and stays near mu forever. So almost sure convergence, which is a strong law, implies convergence in probability. So that means the strong law implies the weak law, but not conversely. So it kind of makes sense why this one's called strong, that one's called weak. So here's a fairly basic example, build some intuition. If we flip a fair coin repeatedly, where we let xi equals 1 for heads and 0 for tails, the weak law of large numbers says that for large n, the running proportion of heads is going to be near 0.5, because it's a fair coin. But a strong law says something stronger, that if you record an infinite sequence of flips, the proportion of heads converges to 0.5 for almost every possible infinite sequence of coin flips you could have gotten. And yeah. Handing over to Zayden for common distributions. If you start like moving stuff around, just like tap.
Okay, we're gonna do common distributions. So luckily you guys get a formula sheet for this. So I will go through the formulas, but I won't prove all of them. It's not really much need, so you don't even need to put this on your cheat sheet because you get the table of distributions, but we'll go through the different distributions. Okay, so first one is the discrete uniform distribution. This one is pretty intuitive. Basically, first of all, it's a discrete one, and every outcome has the same probability. So if you have n possible outcomes, then since the sum of probabilities has to be 1, each one has probability 1 on n. This one is more common, the continuous uniform distribution. This is when you can't really define it as each point has the same probability because the probability of one point is kind of 0 if it's continuous. Instead, you define it on an interval, so something like alpha, beta. And essentially, the CDF is like a flat single horizontal line. So if the interval is like this, alpha, beta, the CDF would be this with value 1 on beta minus alpha. Now, why is that the case? Well, you just need the integral to be 1 if it's a CDF, right? If you integrate from alpha to beta, if you integrate from alpha to beta of this, you're just integrating, well, 1 on beta minus alpha from that interval, and you'll see it'll just get 1. So we denote it like this. X is in uniform of alpha, beta. Okay, now one useful thing, I did say not every point has the same probability because that doesn't make sense if it's continuous. Each one has probability 0. But you can kind of say that there's the length is what gives you the probability. So what does this mean here? Well, if you consider the interval, consider an interval alpha beta, then the probability it's in a given length. So say like the length is epsilon. That's what it means here. The probability that absolute x minus x is less than epsilon. We're just saying the random variable is between, let's say, x minus epsilon. Wow. Okay. So suppose we have x here. I'm going to ignore this. Then this probability will be the same as if we had a different y, for example, and we had between y minus epsilon and y plus epsilon. All that matters really is the length of the interval you're considering. And essentially what happens is the probability will be the length of that interval divided by the full interval. So the length of the interval will be 2 epsilon, so it would be 2 epsilon divided by the length of the full interval, which is beta minus alpha. So you essentially just need the length of the interval you're considering, and that will give you the probability. Now you have these results for uniform distribution. I should mention the support was that interval alpha beta. Then you have the PDF is 1 on beta minus alpha. CDF is there. And the expected value, or the average, is the midpoint of the interval. So alpha plus beta on 2. And the variance is there as well. You also have the moment generating function. These should all be on the table of distributions that you get in the exam. But yeah, this is what I was saying about the length. The probability x lies between a and b. You shouldn't need to do an integral every time you want to do this. You just take the ratio of the length of this interval, so that's b minus a, divided by the full interval, beta minus alpha. So if you have something like this, you don't need to waste your time calculating an integral. It's pretty intuitive. Now we're moving on to the Bernoulli distribution. So this is to do with an experiment where you just have two outcomes, kind of. One you call it success and another one failure. Success happens with probability p, and obviously failure would happen with the complement probability 1 minus p. And the PMF is essentially this. Now, okay, one pretty interesting thing is you can write the PMF as, let's see, px of x equals p to the x 1 minus p to the 1 minus x. And this works for x in 0, 1, as in x equals 0 or x equals 1. This is a bit weird because you have a discrete probability and you have a formula for it. This comes up kind of useful in the second half of the course when you're doing like statistical inference. Sometimes you actually need an expression for the PMF of a Bernoulli distribution. Just knowing it piecewise isn't always that useful. So keep this in mind. You can check that this actually works. You can sub in x equals 0. You'll get p to the 0, 1 minus p to the 1 minus 0. So that's 1 minus p, right? 0 happens with probability 1 minus p. If you sub in 1, you'll also see that it works. So just keep in mind there's an expression for this as well. It's not really useful in the first half of the course, mainly in the second half, but yeah. So here are the standard results. These are all on the table of distributions. Oh yeah, these are pretty useful to know. The expected value is just the probability p, the success probability. The variance is p1 minus p. Okay, now we did already touch on this a bit, but independent IIDs basically is just when you have a sequence of random variables, they're all independent and they're identically distributed, which just means they all come from the same distribution D. And now you can define the binomial distribution, which is essentially you have n trials and n Bernoulli trials, which means you have random variables x1, x2, x3 up to xn. You could say something like you're flipping a dice like n times, and you're asking about, say, the number of sixes you get. Each of those has the same, on a given roll, this is the same probability, right? 1 on 6. They each have the same distribution. And so this counts the number of successes over n trials. So a success could be like you're getting a 6 on the roll. How many 6s do you get? That number is given by a binomial distribution with two parameters, n, p. So n is essentially the number of trials you're doing, could be the number of rolls of the dice, and p is the success probability. So what's the probability you get a 6, for example? That would be 1 on 6. Domain of variation, or the support, is 0 to n, because you can get 0 trials. Imagine you don't get a 6 at all over those n, or you can get 1, 2, all the way up to n. So that's the possible values of x. Then you have this thing. These are the PMF, expected value, variance, etc. And notice how expectation of x is NP. So since x, you can kind of write it as the sum of the Bernoulli trials. Why is that? Because if this is 1 with success, sorry, 1 with success and 0 otherwise, the number of successes is actually just the sum of them. Because imagine you have this one is 1, only this one is 1, the rest are all 0. That's 2 successes, right? 1 plus 1 is 2. So you can write x as the sum of each of these IIDs. And then when you take the expected value, you will actually just get expectation of x1 plus all the way up to xn. And because they're the same distribution, they just collapse into n times the expectation of the distribution, which was np, because about Bernoulli distribution, the expected value is p, and that's why you get np. Similarly, for the variance of a sum of independent variables is just the sum of the variances, and that's why you get n p1 minus p, because p1 minus p is the variance of a Bernoulli distribution, which we went through. Okay, there's one thing. If you have two independent binomial distribution variables, and the n's don't have to be the same, then the sum of them is also a binomial distribution. Now, one way to think about this, if x1 is the number of successes over n1 trials, and then x2 is the number of successes over n2 trials, over n1 plus n2 trials, you can think the total number of successes would just be the sum. But you can also prove it using the MGF. Remember, one thing about MGFs, moment generating functions, is they characterize the distribution. So you don't need to show this using the PMF. You can use the MGF. So one important rule, I don't know if you mentioned it, but if you have two independent variables and you take the MGF of the sum, you can split it up as the product of the MGFs. And the reason is because, well, okay, the reason is because if you have expectation of, sorry. If you have expectation of e to the x1 plus x2, sorry, times s, then you will get to split up. And then one thing was the expectation of a function of a random variable times the function of another one, which is independent. You can split up the expectation. So you can prove it like that. But anyway, if you use the standard MGF for the binomial distribution, which is on the formula sheet, you'll get this. And this exactly matches the MGF for a binomial distribution of n1 plus n2. And it has the same probability p. Okay, now we have the geometric distribution, which is also related to the Bernoulli trials. Essentially, you have, instead of n Bernoulli trials, it's kind of like infinite. You're doing a Bernoulli trial, you're tossing a dice, you toss it a second time, and you keep tossing it. And you're asking the number of them, how many times do you need to toss it to get the first success? So suppose the success is like getting a 6. How many times do you need to toss your dice or your die to get a 6? And that number is given by this random variable x in a geometric distribution. And p is the probability of success again. So it would be 1 on 6 if you're talking about a dice roll and you're asking how do you probability get a 6 or any one or even 1 or 2, whatever. Yeah, so that's the main parameter. This time the support is 1 to up to well, all the positive integers basically, because how many trials to get the first success? Well, it has to be at least 1. You can't have 0 trials and get a success. Or it could be 2 trials to get the success, etc. And one thing is we actually count the trial where you get a success. That's why it's 1 here. If you didn't count the trial, then it wouldn't work. So these are the main results. And what's pretty interesting is I think this actually works for actually no, I'm not sure, never mind. Okay, so one important thing about the geometric distribution is it's memoryless. There's also the exponential one, which is memoryless, but this is the only discrete memoryless distribution. And what does that mean? Okay, this is okay, we have like a quote here. It might be a bit deep, but like the memoryless property means that it doesn't matter how long you've already been failing, the future looks like a fresh start. Like, okay, so basically, even if you haven't got a success, remember, geometric distribution is the number of trials to get the first success. It doesn't matter if it's been 1 trillion trials and you haven't got a success. The number of trials remaining to get the success, it will have the same distribution. So it kind of forgets about the past trials. And what it means in this case, probability x is greater than m plus n, given x greater than m. What does x greater than m mean? It means you've had m trials and still haven't got a success, because the number of trials to get the first success is bigger than m. So given that's happened, the probability that you'll need to wait n more trials is the same as just from the beginning. It doesn't really count. The beginning doesn't really have an effect on the probability. But if you need to put this on your cheat sheet, you could, because this formula might come in handy. Okay, now we have the Poisson distribution. So it's a discrete distribution, and it has a PMF given by this. And the parameter lambda is kind of the overall intensity of the event. So what's this about? It's about the number of occurrences of an event in a fixed interval of time. So say like 1 hour, how many times does an event occur? It's usually a rare event, and lambda kind of represents the intensity of the event. Okay, so Poisson distribution, these are the results. Okay, so sum of independent Poissons is Poisson. I'll actually come back to this later, so for now we can skip it. Actually, okay, I'll go through the proof. So once again, we use the property of the MGFs. You can split it up as a product, only if the variables are independent. And you'll see you'll just get the MGF of a Poisson distribution with parameters parameter lambda 1 plus lambda 2. Okay, this is the Poisson process. So if nt is the number of occurrences of an event in time interval of length t, it actually has the distribution lambda t. So suppose n1 is the number of occurrences in an interval of length 1, and it has Poisson of lambda. That means the intensity is lambda, but consider n half. That's just asking in half the time, how many occurrences do you get? Well, it turns out that it has the distribution of p of lambda on 2, meaning it's kind of half the intensity. In half the time, you're expected to get less, right? Or with less intensity. But if you had double the time, n2, then you'd expect to get more. And the number of occurrences you get in an event, number of occurrences you get in an interval of length 2 would be, well, twice the intensity. So it will follow p of lambda 2 lambda, sorry. Okay, this is a bit different, Poisson splitting. So this is when you can categorize the event into two types. So if n is the number of times a given event occurs, suppose each event can be categorized into type A, type B. Type A is probability P and type B is probability 1 minus P. Then it turns out how many times does type A occur in the same time frame follows a similar Poisson distribution, but the intensity is just the probability P times the original lambda intensity. And similarly for B. Now, to prove this, you can actually use the PMFs. So if you want the probability NA equals K, what does that mean? That means essentially K events occur, K events of type A occur. Now, ideally, you want to know how many total events occur. So what we'll do is we'll condition this on the number of total events. Suppose you know that N equals N total events occur. Then out of those N events, a type A happens with probability P, right? So the first event, it will be A with probability P, second similarly. This will actually form a binomial distribution because you're assuming there's N events. Each one has probability P of being A, and so you get a binomial distribution. Now, if you want the probability NA equals K, you can use the total law of probability. You just condition it on N equals N and sum up over all N. So if you remember this was the law of total probability or whatever. And because given N is equal to a given N, so like N equals 5, you know that it will have a binomial distribution of 5 and then P. So bin of 5P, for example, right? But in general, this is just summing up over all N. And notice we start the sum at K. The reason is, well, we're assuming there's K events of type A. So suppose K is like 3. I can't assume there's only 2 events because I can't have 3 events of type A. You need to assume you need to assume that the N is greater than or equal to K. Because if you want K events of type A, there needs to at least be K events total, if you know what I mean. Anyway, you sub this in, and sorry, this got cut off a bit, but the probability N equals N, well, N was a Poisson distribution, so this is like e to the minus lambda, lambda to the N on N factorial. And now if you want to find this sum, there's quite a lot going on. The index variable is N. So technically anything that doesn't depend on N, we can take out the sum. So I'll take out this stuff. And you're left with this. Now what you can do is, this is kind of similar to the exponential Taylor series, but that starts at 0. So we'll just do an index shift. You can subtract K from the index and replace N with N plus K in the actual formula, and you'll get this. Now, well, lambda to the K, that doesn't depend on the index variable N, so we can take it out. So what you actually get is, let's see, e to the minus lambda, p to the K on K factorial, lambda to the K. And the rest of it will just be, well, you can kind of see it here. It will be lambda times 1 minus p to the N over N factorial. That's the exponential of 1 minus p lambda. And if you actually cancel this out here, you'll see you'll just get this. And this is also actually, just the PMF of a Poisson distribution with p lambda as the variable. So that proves that NA has a Poisson distribution of p lambda. And you can do something similar for B. Okay, we'll just go through an actual question now where this comes into play. A website receives an average of 20 visitors per hour. and each visitor is independently probability 0.2 of making a purchase. So 0.2 of making a purchase and I guess 0.8 of not making a purchase. So if 10 visitors arrived in an hour, what's the probability that 2 of them made a purchase? Well, this is kind of a trick question. It's just a binomial distribution because you have 10 visitors and then each one makes a purchase probability 0.2. So it's technically just the binomial PMF and you just sub in the values. So it's essentially 10 choose 2, 0.2 squared, and then 0.8 to the 10 minus 2, I guess. Now, what's the probability in a given hour? Exactly 5 visitors make a purchase. So this is saying what is probability NA, like as before, the probability that the event number of people making a purchase is 5. So what we showed is this has distribution P lambda. Here P is 0.2. So it's 0.2 times lambda. Now, I should have mentioned what is lambda here. Well, we're assuming it's a Poisson distribution, even though it doesn't say, because this is kind of a rare event and it's talking about a given time frame per hour. So you can assume it's a Poisson distribution. One thing that's important is it has the same expectation as its parameter. So the expected value of a Poisson distribution of lambda is actually just lambda. So when it says average of 20, that's the expected value. It should also be, that should actually be our lambda. Because if x is in, let's see, x is in Poisson lambda, then that implies expectation of x equals lambda. That's just one of the results. So we're assuming it's Poisson of 20. But then for b, it will be Poisson of 20 times 0.2, based on the Poisson splitting that we showed before. And then you can just use the Poisson PMF and calculate it. Now, how about for C? What's the probability in a given hour at least 3 visitors make a purchase? What does that mean? That means, well, if we call it NP, I said, that's just asking that NP is greater than or equal to 3. Because, well, that's the variable of how many people make a purchase. And then you can use that, use the complement because it's easier, because you only need to sum 2 probabilities, I guess 3. And you use the Poisson PMF to find these values. Okay, exponential distribution. So this has this PMF, and we write it as exp of lambda. The support is 0 to infinity. And yeah, so this is pretty much it. What does it represent? It usually represents the amount of time until the first occurrence of the event. This is similar to geometric distribution. I talked about the number of trials to get the first success. This instead is a continuous version, the amount of time to get the first success or occurrence, I guess you could say. And it's related to the Poisson distribution. Now, to prove this, you can use this approach. T is greater than T, if and only if there's been no occurrences by time T. What does that mean? Well, the amount of time until the first occurrence. If that's greater than T, then in the first T units of time, we haven't got an occurrence. So that essentially means nt equals 0, where nt is the number of occurrences in the time frame t, a unit length t, I guess. And then if 2 events are equivalent, that means you can take the probabilities and they should be equal. So using that and using the fact that nt is from Poisson lambda t, you can use the PMF of that and you'll get this. If you rearrange it, you get the CDF is this. Notice I did 1 minus, essentially, this is the complement survival function, you can say. Probability t is less than or equal to t is 1 minus the probability t is greater than t. That's where this comes from. If you differentiate this, you'll get this result, which is the same as an exponential distribution. Okay. Yeah, so amount of time until the first occurrence is given by exponential distribution, and also for the waiting time between occurrences. This is actually pretty important. So it's kind of to do with the memoryless property. It doesn't really matter about what's happened in the past, only between consecutive occurrences. That's also an exponential distribution. So these are the results. And yeah, so this was the memoryless property. It also holds for exponential. Geometric has this as well. These are the only 2 distributions which have this property. And we have this result, which looks kind of weird, right? What it means is given that t is greater than t naught, so you've waited t naught amount of time, you haven't got an occurrence. Now, assuming that, what's the distribution of t minus t naught, which is actually the remaining time? Because if you've had t naught time passed already, suppose this is t naught, then imagine that it took time t to get the first occurrence. The remaining time until the occurrence is t minus t naught, right? And that has the same distribution as t, because it doesn't really matter that you've waited t naught amount of time. It's memoryless. An example question is here. Basically, you have customers entering a store, and they each spend an amount, which is given by a random variable, which is exponential distribution. And you're given that the customer spent more than 50. So given that information, what's the expected amount that they spend? Well, this is an exponential distribution. So if you're told they spent more than 50, that actually doesn't affect the affect how much they spent. So if y prime is the remaining amount they spend, so they spent more than 50, what's the total amount? Well, whatever that is, we'll set y prime to be, well, y minus 50, if y is the total amount. Then this is the remaining, unfortunately, it's not time here, it's more like amount spent, but it's the same idea. This is the remaining amount they have to spend. It has the same distribution as the original amount y. So you need to calculate expectation of y given y greater than 50. You can technically kind of do a plus minus thing. You can do y minus 50 and then plus 50. And the expectation of a constant is just itself. So this will just give you 50. And y minus 50 given y greater than 50 has the same distribution as y. So it's the same as the expectation of y. And you get expectation of y plus 50, which is 70 because it was an exponential distribution of parameter lambda 1 on 20. One of the results is that the expected value is 1 on lambda for an exponential distribution. So 1 on 20, which is 20. Okay, then we have the gamma distribution. Here, gamma is the gamma function here, and it's kind of a generalization of the factorial. Unfortunately, gamma of n is not n factorial, it's n minus 1 factorial. But yeah, if you need to put that in, that might be useful. Gamma distribution has these properties. Okay, yeah, and then this is actually related to the exponential distribution. A sum of independent gammas, independent exponential distributions is from a gamma distribution, gamma of n lambda. We're gonna collate all of these to the end of the chapter, this result about summing different variables of given distributions. So you can take a photo of that later or whatever. We'll upload the slides as well. But yeah, the way you prove this, as usual, is with the MGF approach. Because they're independent, you can split up the MGF of the sum as the product of the MGFs. And if you quote the MGF for the exponential distribution, you'll see that it doesn't depend on I, the index variable, and you can just take the product normally. And this actually is the MGF of gamma and lambda. Wait, what? Okay, I think I was meant to cut this out. Okay, normal distribution. So this is the normal distribution. It has PDF 1 on root 2 pi e to the minus z squared on 2. Or you can use x for the variable, but it doesn't matter. We use we use phi for the PDF and capital Phi for the CDF. Unfortunately, the CDF doesn't have a nice formula. It's not really useful to know this, but you can just, this is kind of just integrating from minus infinity to z, which is how you define a CDF anyway. But yeah, it doesn't have a nice formula. It does have some nice results, which we'll go through. First of all, the standard normal distribution, which is what I've showed you here actually, it has expected value 0, so average, mean 0, variance 1, and we have these. There's a more general normal distribution, which is 1 on root 2 pi sigma squared, e to the minus this. Technically, you can say like e to the minus x minus mu over sigma squared on 2. So the original one was 1 on root 2 pi e to the minus x squared on 2, right? Here you're replacing x with x minus mu on sigma. And this is an normal of mu sigma squared. this has mean mu and variance sigma squared. So the parameters are basically telling you what the mean and variance are. Okay, here are some important properties to note about the PDF and CDF. First of all, the PDF is even. You've probably seen this picture before, but I think it looks something like this. This is the PDF of the normal distribution. It's an even function. The CDF has this nice property. So phi of minus z equals 1 minus phi of z. Bro, what? Yo, what happened to the slides? Oh, okay, so linear transformations of a normal variable. This is one of the pretty useful properties. If you have ax plus b, where x is normal, then it's also normal. And to find the parameters, you just take the expected value and variance, because the parameters of the normal distribution are just those. So you can prove this using the MGF approach, and it's pretty simple. It also works when you have, okay, I'll just go back to this. Notice here it's just ax plus b. So just one random variable x. Here you can also have a1 x1 plus a2 x2. As long as they're two independent variables, this also will be normally distributed. And the variances and mean just go with that. If you take the variance of this, you can see you'll get a1 squared times the original variance of x1 plus a2 squared times the original variance of x2. That's because the variance of a sum is the sum of the variances when they're independent. Once again, you just use the MGF approach. If you need to do this, you should just look at the table of distributions and the MGFs, because you don't need to memorize them. Okay, I think it's just loading. Central limit theorem. So this essentially says that if you have a random sample, which is essentially, random sample just means you have n IID random variables, then Zn, which is 1 on root n, it's this weird expression, approaches a standard normal distribution. The more useful case is usually one of these. It's important to know these. The sample mean approaches a normal distribution, and the sum of variables approaches a normal distribution. If you need to remember what parameters are in these distributions, just take the expectation. I mean, you could just put on your formula sheet, but the expected value of the sample mean is just mu, and the variance is sigma squared on n. So that's why you get this. This is really powerful. So you can approximate a distribution of the sample mean or the sum of the random sample with a normal distribution. That's essentially what it's telling you here. Okay, you might want to take note of this. So what's pretty nice is a lot of these common distributions work with linear transformations. If you have a uniform distribution and you take it like alpha u plus beta, it'll also be uniform, and it's kind of just intuitive, as in the result is intuitive. You'll get another uniform distribution with the interval having moved by like multiplied by alpha and beta. This only works if alpha is positive though, because if it's negative, the order will be a bit switched. So yeah, and we're assuming A is less than B. If you have Bernoulli distribution and you have independent IID variables in Bernoulli of P, then the sum is a binomial distribution. We kind of went through this. If you have independent binomials where the n's are different, you can say ni for each one. So not identically distributed this time necessarily. The sum of them is in this distribution, binomial of the sum of the n's and then p. If you have independent Poissons, you also have this. It doesn't have to be IID, it doesn't have to be same distribution. The lambdas can be different. Exponential, we went through this. Oh, this is also a pretty interesting one. If x is exponential of lambda, then ax is exponential of lambda on a. And you can try proving all of these with MGF and stuff. There's also this result for gamma. And the normal one, which we went through. This is pretty important. Okay, we'll just go through some questions. So suppose you make 1,000 rolls of a dice and they're all independent, and you're given the number of sixes appears 200 times exactly. Approximate the probability the number 5 appears less than 150 times. Okay, so you've had 200 rolls which gave a 6 exactly. So I guess 800 remaining rolls. Out of those, none of them are 6s. That's what we're saying, because 1,000 is the number of total rolls. So, okay, okay. So if you have 800 rows and you're asking about the number of five, how many times do you get 5? Is that less than 150? What's the probability of that? Well, out of the 800 rows, well, this is kind of a binomial distribution because each of those 800 rows will be a number 5 with probability 1/6, right? So if x is in, you can kind of say x is in binomial of 800 times 1 on 6, with 1 on 6, then you're essentially asking what's the probability x is less than 150, where x is the number of 5s that's appearing. But this is kind of a given probability, given that the number 6 has appeared 200 times. So you technically need to have this condition. Yeah, so, oh, okay, yeah. So that was my mistake, actually. I forgot the conditional probability. This is only like if you don't assume the condition, but you have to account for it. What's the probability it's a 5? We already know that it's not going to be a 6. We said out of these 800 rows, it's not a 6. So technically, the only possibilities are 1, 2, 3, 4, 5. Can't be 6 based on the condition. So it shouldn't actually be 1 and 6. That was my mistake. It should be 1/5. So x now is in binomial 800 1/5. And you're just asking what's the probability it's less than 150. So then approximating it with a normal distribution, which actually I should have explained this. The binomial distribution approaches a normal distribution. One reason to argue that is this here. Here, okay. Binomial distribution is a sum of xi's. It's a random sample, right? So yeah, so one thing about the central limit theorem, remember it tells you that the sum of xi's of an IID sample will approach a normal distribution. So that's why the binomial distribution will actually become normal approximately as n goes to infinity. I think there was something in one of the class tests, the first class test. If you look at the past papers, it'll have a question on this, explaining why you can approximate a binomial distribution with the normal one for large n. But yeah, so with that approximation, it's you essentially take, if z is a standard normal variable, it's z less than x minus mu over sigma, 150 minus the mean. What is the mean of x? It's a binomial distribution. The mean is np, 800 times 1/5, which is what, 160 or something? Right, how do I know this? Okay, I think it's 160. And then over sigma, which is np 1 minus p. And you can calculate that for yourself. It should give this. And this will give you this. And in the exam, they'll probably give you a value for this, which you need to calculate. So you don't need to, yeah, so that should be fine. Okay, next question. Imagine you have a stock where if the present price is S, after one period, it will move to this times S with probability 0.52 or 0.99 S with probability 0.48. And now somehow you need to find the probability the stock price will be up at least 30% after the next 1,000 periods. Okay, so what does that mean? Well, okay, so over the next 1,000 periods. So we need to introduce some sort of random variables. We know that the price goes up, 0.52%, 0.52 of the time, 52% of the time, right? So if x is the number of times it goes up, stock goes up, and y is the number of times, what the hell? Okay, yeah, that's fine. Okay, if y is the number of times the stock went down, then can we relate x and y? Well, there's 1,000 periods, right? And if this is the number of periods that it went up, you can see the x plus y should be 1,000. Now, somehow we need the probability the stock price will be up at least 30% after all this has occurred. So assuming it starts off at like S0, then if it went up x times, you can think of it as multiplying by a factor of 1.012 x times. And so that's like 1.012 to the x. And if it went down y times, it will be what, 0.99 to the y. This should be the price at the end of all those periods. Like if you can take a bit of time to go through this on your own, but Now this, we just need this to be 30%, at least 30% more than the original price. So yeah, so you have this. This should be greater than or equal to, I guess, not 30% of S naught. It should be, well, 130% of S naught. So I guess 1.3 times S naught. Because 30% of S naught is not an increase. You need 1.3 to be a 30% increase. It's a bit trippy, but yeah. And then once you do that, you just need this. Now you're essentially asking the probability of this, right? Well, use the fact y is 1000 minus x, and you'll get this. And if you just do a bit of rearranging, you can solve for x. Like, I won't go through the details because these numbers are kind of terrible, but you get x greater than or equal to this. So x is an integer, right? So technically you can say x greater than or equal to 470, and then approximating with the normal distribution. Wait, what is this? Yeah, approximating with the normal distribution, you'll get something like this. Okay, now suppose x is in x of 1, and y given x equals x is a Poisson distribution. So when you know the value of x, y will have a Poisson distribution of x, basically, and you want the PMF of y. So what is the PMF of y? You're asking probability y equals y. Now, there's actually a total probability law for continuous random variables. You've seen it for discrete, right? But you can actually write it like this, where instead of this being a sum and this being probability x equals x, you can actually do it with the density. This is kind of worth knowing. So this allows you to have conditional probability and write y equals k in terms of a conditional probability, because we know the conditional distribution. So that's why this is kind of motivated. Then, because this is a Poisson distribution, you just sub in the PMF of the Poisson random variable and this, and eventually, if you do a substitution here, u equals 2x. This is actually the gamma function. This is gamma of k plus 1 or k factorial. Or you can relate this to the gamma distribution if you need to, but yeah, well, it's important to know, it's kind of useful to know what the gamma function is because they have defined it in the course. It's just k factorial, and you'll see you'll get this. Okay, also, if you need to revise your midterm papers, yeah, so all of them were uploaded onto Moodle. You might not have seen all of the midterm papers for this term because there were 6 different ones, and we also have made solutions to the papers in the Discord server. So you can use those to revise. And yeah, okay, transformations topic. This should be the last one for today. So we have some PDF transformations. Essentially, if you have a random variable x and do x plus b or ax plus b or ax, you'll have these results here. We won't go through all the proofs, but the whole idea is you start off with the CDF because the CDF gives you a probability, right? If this is a density, you can't exactly relate it to a probability. So you start off with the CDF. You start off with the probability that ax is less than or equal to y, if we're calling y equals ax. Then essentially you just rearrange this. And now this is just the normal CDF of x at y on a. Now, if you want the density, you just differentiate this with respect to y. And that's what you get. You do get an absolute value here, which is a bit annoying. It depends on the sign. But yeah. Yeah, so maybe it's useful to note these down because we don't get these like on a formula sheet or anything. Put these in your cheat sheet or something. PMF, we have a similar thing, except there's no factor outside. It's just px of y on a, px of y minus b, etc. This better load. Okay. Okay, so we'll go through some transformations. First of all, invertible transformations on discrete. So if phi is an invertible function, this is essentially when you're taking a function of a random variable. If phi is invertible, it's actually not too bad. The probability y equals y is the probability x equals x. What does that mean? I'm saying x here is whatever value that phi of x equals y. So whatever value of x which y comes from, if you know what I mean, from the function. But yeah, in general, you can just write it like this. The probability y equals y is the probability x is phi inverse y. Because phi is invertible, we can do it like this. So now why does this work? Well, if y equals y, well, y is phi of capital X, then you can just invert both sides. Phi is invertible, that's our assumption. And then, okay, yeah, so then x equals phi inverse y. Now, the support, pretty important to note, the support of the new variable is phi of the original support, which just means you apply phi to each of the variables in the original support. So essentially you have the same probabilities kind of, you're just relabeling the support, if you know what I mean. Okay, now we have continuous transformations. You have a similar result. Unfortunately, there's going to be a correction factor, which is this here. Or you can write it in this form, they're equivalent. So similarly, the support will transform to be phi of the original support. We'll go through some examples, so we won't go through too much on this. Once again, you prove this from the CDF. You essentially just get this. Instead of, yeah, you get this, and then this is the original CDF at phi inverse y. If you differentiate this, it will be fx of phi inverse y with respect to y times the derivative of this thing, because it's a chain rule, right? And the derivative of that thing with respect to y is actually this correction factor. Now, by the way, one thing to note is this implies this only when it's increasing, only when phi inverse is increasing. If it's an increasing function, then you can preserve the inequality sign. Otherwise, you'll actually have to switch the inequality sign here. And one thing to note is if phi is increasing, so is phi inverse. And if phi is decreasing, so is phi inverse. But yeah, you can really just know the formula. So an example here, clearly the exponential is invertible. So if x is in uniform 0, 1, find the density of e to the x. So what is that? Well, you can actually just use the formula fy of y should be fx of the inverse. Well, the inverse of the exponential is the log, right? So log y times the derivative of this log y, which is 1 on y. You need the absolute value, but y is going to be positive. It's pretty important when you do these transformations to think about the support of the new variable. Sy equals what? Well, you just take e to the support of the original one. The support of the original variable is 0, 1. If you take the what is it, the exponential on this, we'll just get what? E to the 0 is 1, e to 1. So this should be between 1 and e, right? So let's see. Do I actually write this? Yeah. Okay. So the new support is between 1 and e, it's this interval, and therefore y is going to be positive. So we don't actually need the absolute value technically here, but you should keep it in general just in case. Now, x is a uniform distribution. One thing to note is the standard uniform distribution has PDF is just 1. So technically this just goes away. Like you don't really need to worry about the fx term. It's just 1. So fy is just going to be 1 on y. And the support is 1e. By the way, if you're in an exam and you just want to check your answer, you should check that it actually does integrate to 1. Because this should be a density, right? It should integrate to 1. This is going to be log e minus log 1. You can check that. And that's just going to be 1 minus 0, which is 1. So if your integral doesn't equal to 1, you know you've made a mistake. Just use that as a sanity check. Okay, now density of minus log x. So this is an invertible function. Like the graph is just going to be what? Like this, I think. Something like that. Oh, okay, right. That's fine. So what is the graph of this? Well, this is the log x graph, right? So this one should actually be like this. Okay, and this is at 1. But yeah, this is just the injective function. One thing I mentioned, I said invertible, injective. Technically, for our purposes, we can just say injective because the difference between those is actually the codomain. Well, codomain doesn't really matter. You can define it to be the range. Technically, you just need it to be injective or monotonic or invertible. Any of those would suffice. Okay, so then the support is just going to be 0 to infinity because you're taking minus ln of 0 to 1. Okay, so yeah, so I should have actually drawn this only for 0 to 1. Something like this. And yeah, so you just use the formula and it basically falls out. Okay, so now, yeah, sure. Here, Jimmy, can you get a mic? Do you have one? Okay, there should be one. Yeah, sure. Oh, yeah. No problem. No problem. Okay, so now we have the inverse probability transform and the probability integral transform. So these are in the notes. Basically, if you take the quantile function, which is kind of like the generalized inverse of the CDF, and you apply it to a uniform distribution, you actually get the original distribution back, which is pretty weird. Basically, it means if you generate uniform random numbers, which is easy to do in practice because the uniform distributions is nice to work with, then you take the inverse CDF or the quantile function in general of those random numbers, you actually get a new random quantity from the same distribution. So this allows you to basically generate random variables of whatever distribution you want. All you do is, as long as you know the quantile function, you can just apply that to any uniform distribution and you'll have variables from that distribution D. This one is kind of more useful in like for the exam, I'd say. If you have a continuous random variable and you apply the CDF of it to the variable, which is a bit weird, you'll see what it looks like, then this actually follows a uniform distribution, the standard one. So something like this, find the density of y given this. Can you try to see what's happening here? What's the CDF of x of 1? Well, it's actually 1 minus e to the minus x, right? Yeah. For a given domain 0 to infinity. Okay, for a given domain. Now you're applying that to the random variable x. So technically this thing here is actually a uniform random variable. So we can write, sorry. So you can write y equal to u to the 10, where u is a random variable in the uniform distribution. So here, that's what I've done. And now if you want the distribution of it, you can do the CDF approach, start with the probability, and you can just take 1 on 10 of both sides because that's the increasing function. And then you just get this. Now, one important thing to note, the uniform distribution, the CDF is like it's x, you can say fx of x equals x for a given domain, kind of like an identity function. So this is actually just y to the 1 on 10. So differentiating this, you'll get this here. Oh, sorry. Differentiating this, this is what you'll get. And the support, this is actually an invertible function, and you can check the support will be 0 to 1 just by applying it. So it will be like, well, 1 minus 1 is 0. So that's the 0. And if you take x equal to infinity, if you take x to infinity, you'll just get 1 minus 0 because each of the minus infinity is 0. You'll get 1 to the 10. So that is the support. Or you can technically, it might be easier to just say y equals u to the 10. So the support is, I guess, the support of u to the 10, if you know what I mean. So it will be, it's just 0, 1. It will be 0, 1. For each of those, you raise to the power 10, it will be between 0 and 1 as well. Okay, let me move this out. Okay, so this is kind of more annoying. If it's not invertible, you can't just do that. You actually need to do a bit more. Let's see. So you have this result, which looks really weird, but what it just means is the probability y equals a given y is you sum up over all probabilities which map to y. Now, what on earth does that mean? I'll just go through it here. Suppose x1, x2, all the way up to whatever, are all the elements in x, support of x, which map to y. What does that mean? It just means like phi of x equals y. If it's not invertible, this isn't a unique x. There could be x1, x2, it could be many. But suppose these are all of them, then the probability y equals y, well, it's the same as the probability x is one of these, right? Because these are the only values such that phi of x equals y. So it's the same as this. And because it's a discrete thing, we're assuming also these are all distinct numbers, x1, x2. You just sum up over the probabilities of each one. Probability x equals x1 plus the probability x equals x2, etc. In practice, you kind of just use this intuitively. But yeah. Okay, this is kind of cooked. So imagine x is a discrete random variable with this support. The PMF is this, and y is given by this cubic, and you want the PMF of y. Unfortunately, you kind of just have to do each one. So first of all, the support, you just apply phi, the function phi to each of the elements of the support. And if you calculate it, you'll get these numbers. But obviously, you don't need to count 4 twice or 2 twice or 0 twice. The support is going to be this thing. These are the only possible values of phi of x. Now, if you want the PMF, you just need the values of y at a given value in this sy, right? So you just try p of y equals 0, p of y equals 2, p of y equals 4. And you need to think, when does y actually equal to 0? Well, in our table, it's when x equals -2 or x equals 1. So you add those up, the probability x equals -2, probability x equals 1, and that's given from this, which you can calculate for yourself, but you get these values, and I think you get the idea. You can do it similarly for these two. And that's good enough for a PMF because you have the support and you have the probabilities. Okay, so find the PMF of y equals floor of x on 2 if x is a geometric variable. Okay, let me just see. Okay, so first of all, the support, you technically need to think, how does this work? The original support Sx is, let's see, 1, 2, 3, up to infinity. If you take the floor of x on 2 for each of these, floor of 1 on 2 is 0, floor of 2 on 2 is 1, floor of 3 on 2 is 1, because it's floor of 1.5. Wait, is that right? Yeah, it should be. Then floor of 4 on 2 is 2, and etc. You can see the support is just going to give you 0, 1, 2, 3, etc. You can kind of get the pattern. So the support of y should just be 0, 1, 2, etc. Basically, you just apply this function to each value in the Sx. Now, we want to find the density, the PMF of this. So P of y equals k. Okay, let's see. So what does that mean? It means the floor of x on 2 is equal to k. Now, one thing to know about the floor function equaling a number, for example, let's just say floor of y equals 3. When does that actually happen? Well, it's when y is between, like, what? You can say 3, actually, let's read the other way. It's between 3 and 4 exclusive, right? Because if you have like 3.5, for example, then that should give a floor of 3, right? So in general, x on 2, when you floor it, e equals k if and only if you have this result. So now because, okay, you can multiply by 2, right? You want to write it in terms of x. You have this, x is between this. X was an integer, by the way. The geometric random variable is an integer. So it's between 2k, 2k plus 1, 2k plus 2. We don't include this one, okay? Because we have a less than here. You only need to focus on these two. So in general, y is equal to k if and only if x equals 2k or x equals 2k plus 1. So that's why you can sum up the probabilities and you'll get this. Now, there is an unfortunate edge case here, which is a bit cooked, but this assumes k is not equal to 0. You can also see this formula is a bit weird if k equals 0, because you'll get like, well, 1 on 1 minus p here. So if k equals 0, what does that mean? Floor of x on 2 equals 0, right? Now, you can test the values. You'll get x equals 1 would work, right? Because floor of half is 0. X equals 2 wouldn't work, because that will give a floor of 1. Anything else won't work. So technically, it's actually just x equals 1. That's the one case where you have only one value of x mapping to 0. If you kind of know what I mean. So this is just p. You can just sub into the geometric PMF to figure that out. And you get this weird expression. Okay, for continuous, it's unfortunately even more cooked. So you have this weird expression, but once again, it's similar. You sum up over all intervals where y is achieved. What does that even mean? Well, if the function is phi, it could look really weird. It might not be invertible, but you can kind of partition it into places where it is invertible. Let's just look at a simple example like this x squared. Sorry. X squared is not invertible, right? Because it's not injective. Okay, what's going on here? But you can split it up into places where it is injective. Just two intervals, for example. First one would be like this and this. Obviously, for minus infinity to 0, it's going to be invertible. And for the other half, it will be invertible. Now, the probability, the density that y of y is where you sum up over all the intervals where y is achieved. So if I'm talking about y equals like 1, for example, y is going to be achieved twice in the first branch and in the second branch. So you sum up over all branches. In fact, I'll just go through an example, but there's also a correction factor, which is the derivative of the inverse at y. Oh yeah, another thing to note is you can write it like this because if you remember, derivative of an inverse is 1 on phi k prime of the inverse. And the inverse is going to be xk. This is essentially just the value in that interval. You know what? I'll just go through an example because it's a bit of a weird formula. Okay, simple example here. X is in standard normal distribution. So it's like this. This is the support of x. In fact, the support of x is actually the real line. I'm just going to graph y equals x squared actually, not the... Okay, that's not symmetric, but that's... Okay, so now we need the density of y equals x squared. Once again, like as I showed, you can split it up into these two intervals. So then fx of x, fy of y equals the sum over each of those intervals where it's achieved. So any y is going to be achieved in both one, right? So it's fx of, and now here you say the inverse of it, that is, which is achieved. So technically you can say if y equals y, like you can say x squared equals y, right? X equals plus minus root y. So if I have minus root y here and root y here, you can see these are the values in terms of y, such that when you square it, you'll get y, right? So you apply this here, and you apply here the derivative of that branch, which is derivative of minus root y, and take the absolute value, which is just 1 on 2 root y. And plus fx of root y, again, derivative of root y will just be 1 on 2 root y. So in this case, you actually get this nice result. And you can use whatever the PDF of x was with the standard normal to get this. Okay, again, let's try this. This is a bit harder example. So we have minus 2 to 3 and absolute x. So here it's actually a bit more confusing because you need, for example, if I have y like this, let's see. Suppose y is less than or equal to 2. It's going to be achieved on the left and the right in both branches. Like, first of all, you define which branches. It's going to be invertible from minus 2 to 0, right? In this branch, you can see it's invertible. On this branch, it's also invertible. If y is less than or equal to 2, it's achieved in both branches. So keep that as a single case. So for y in 0, 2, it's fx of minus y because, oh, what the? Okay, so let's see. Yo, where'd the page go, bro? Okay, technical difficulties, trust. Give me a second. Bruh. It's just gone, bro. Wait, literally just disappeared. Yo. Thank you, bro. Okay, we're back, we're back. So for y in 0 to 2, it's achieved twice, and because it's y equals absolute x, it's going to be achieved at what, minus y and y, right? Because this implies x equals plus minus y. On the left branch, it will be minus y. So this is what we have here. Fx of minus y times the derivative of this thing, absolute value, by the way, plus fx of y, derivative of this thing. And because x is actually a uniform distribution, these both are just going to be 1 on 5 because that's the, like 1 on 3 minus minus 2, if you know what I mean. That's the PDF of the uniform distribution. And these are both going to be 1 because you're taking the absolute value. Derivative of minus y is minus 1, but you take the absolute value. Now, this is only for 0 to 2. What if you have y is like, y is here, for example? It's only achieved in this branch. So you technically only need one term in your sum, and it will only be for that branch there. So okay, yeah. So for this one, you only sum up over the positive branch. So it's y which gives it. So y equals absolute x. If absolute x equals y, you'll have x equal to y because we're in the positive branch. It won't be minus y. And then you just take the derivative. So you need to do a case-by-case basis, usually by drawing the graph. Okay, I'll try to go through this one quickly. Find the density of sine x if x is uniform 0 to 2 pi. So you first need to split up the graph of sine into parts where it's invertible. So it would be from this, this, and this. So this is what, 0. Oh, it's actually moved. This is going to be what, pi on 2. And then this is 3 pi on 2. And this one is 2 pi. So these are your 3 intervals where it's invertible. And yeah, so that's going to work. Now, for any y in 0 to 1, by the way, the support of this is just going to be whatever range of values that sine of x will take when x is in the support of this. So it takes on values, well, minus 1 to 1, right? Because sine is between minus 1, 1 for these values. So this is our domain of variation for sine of x. And for any of those values, we need to see when y is achieved. So if y is above the x-axis, so if y equals like what, half, for example, it will be achieved in the first branch and the second branch. So for y in 0, 1, that's why we have 2 terms in our sum, because it's only achieved in these first 2 branches. Now, what am I even doing here? Well, if y equals sine x, sorry, then what's the derivative of the inverse? Well, it's 1 on f prime, so phi prime, which is cosine, of whatever solution this is. Let's say this is x1, and let's say this one is x2. That's why I have this thing here, and this thing here. But ideally, you want to write these in terms of y, right? We don't want to have random x1s, x2s appearing. So we do know that, if that's the solution, like y equals sine of x1, we know cosine of x1, absolute value, it will be like what? Root 1 minus y squared, right? Based on the sine function, because absolute value cosine is root 1 minus sine squared. So it'll just be root 1 minus y squared. We don't even need x1 really. So these terms actually become this here. And then here I'm just using the PDF of the uniform distribution and we get this. Now for y in -1 to 0, so that means I'm just talking about, let's see, talking about this here. For y in any here, it's going to be achieved by branch 2 and branch 3. Yeah, it should be. So you'll actually just get a similar thing. You'll get something like this, and these error terms are like I guess the factor you multiply by will just be the same. So you actually still get 1 on pi root 1 minus y squared. Okay, so distribution of x plus y. Okay, so this is actually a pretty useful formula to note. If you have x plus y, which is two random variables, they don't even have to be independent, then this is what happens. You have fx of y at x, and then z minus x. So this is a bit weird, but you can kind of think of it as like, let's see, z. Okay. So z equals x plus y. So y equals z minus x. And I guess for the independent case, so I'll just go, it's easier to explain. Then the probability or the density is of, let's say, sorry, f sub z of z is, well, kind of like you average it out. You assume you have fy of a given y. I think I'll go with this. Okay, sorry. You kind of average out at fx of x and fy of y, which would be z minus x, and you integrate this. Well, actually, we can go through a proof later, but it might not be that useful. It kind of uses the Leibniz rule, but yeah. Now, you might think this is a neat formula, but it's kind of annoying because even though it's integral from -infinity to infinity, it will collapse to something smaller because of the support. And that support might be a bit difficult to find, but we'll go through that. In general, you also have these formulas, which you could put on your cheat sheet, but I'm not sure how important this is. It's kind of more, you can always actually use a trick to just use the x plus y instead of this, which we'll go through. Yes, this, okay, yeah. So if you have x and y, in this case, they're independent, it makes things easier. Then 2x plus y, how do we find the density of that? Well, one thing you could do is let like v equal to 2x. Now z is just v plus y, it's just a sum of random variables, right? So one important thing to note, if x is in uniform 0, 1, then 2x is in uniform 0, 2 times 0 times 1 times 2. I think we went through this, it's one of the transformations. So v is actually in uniform 0 to 2. Now, because they're independent, you have this result. fz of z is the integral of fv of z minus y times y. The important thing is these two should add to give z, the two arguments. Now, yeah, this is actually a bit more cooked. The hard part of this is always finding the support of the transformed variable. It's not actually the density. Now, for this to make sense, we want z minus y to be in the support of v and y to be in the support of y. So using that, we need this and this and this. Now, because y is in 0 to 1, you also need this. So you get some weird result here where y is between max of z minus 2 and 0 and min of z and 1. So now what? Well, you essentially need to calculate this integral for values of z, but like you don't know what they are unless you take cases on what max, on the max and min, right? Okay, so we'll go through a first case where z is in 0 to 1. Then max of z minus 2, 0, you can calculate it, it will be 0, and the minimum will be z. So the bounds are y is between z and 1. So that's what you integrate between. Sorry, 0 and z. So you integrate between 0 and z. Where does this half come from? That's actually just the PDFs. FV is uniform 0 to 2, so we'll have PDF half. Y was uniform 0 to 1, so we'll have PDF 1. That's why it's just half times 1. And you integrate it, you'll get this. Now, if z is in 1, 2, the maximum will be 0 and the minimum will be 1. So you know the bounds of integration will be 0 to 1. And you can do similar for the third case. What I should mention is the support is going to be actually pretty nice. If this is in 0, 2, and this is in, what was it, 0, 1, the support is just 0 to 3. So we only need to check z up to 3. And you get this when you do the integration. So you get this. And if you have time, you can check that this actually integrates to 1. But yeah. Okay, so this is to do with the Jacobian. I think this wasn't talked about too much in the lecture, but we'll still go through it. So this is when you have two variables, transformed versions of x and y. So you have x, y, and then you have new variable u equals something in terms of x and y. So it could be x plus y, b equals x minus y, for example. And you're asking about the joint density of the two new variables in terms of the joint density of the two original. And it's actually pretty similar, except now you just have a determinant of a Jacobian. If you've done 2111 or 2011, yeah, then you'll know what this is. But we'll go through a simple example. So suppose we have this is the joint density, and we need the density of UV, joint density. So it's going to be FUV of UB is equal to Fxy of xy times the absolute determinant of the Jacobian. But what is the xy? We want to write it in terms of u and v, right? Technically, if you want a formula for this, why would there be an x and y involved? So it's actually in terms of u and v, because if u equals 2x and v equals y squared, then the x is actually just u on 2 and the v is like kind of like square root y, because v is going to be positive here. So yeah. And y is also, yeah, y is also positive. So I'll just show you, this is where, I don't think they've written it. Okay, the hard part is finding this correction factor as well. So essentially you take u equals to x, v equals y squared, but you write it in terms of x. So I think I already wrote this. It will be x equals u on 2 and v equals root y. Now the sorry, this is meant to be y equals root v. Okay, so then what you do is you take the Jacobian of this, and this will end up being something like this. You differentiate the x with respect to u. So the first component, this will be half. Then differentiate with respect to v, but derivative of u on 2 with respect to v is 0. And differentiate y now with respect to u, which is the first variable, will be 0. And if you do it with respect to v, you'll get 1 on 2 root v. This is what this weird expression is here, because x is something in terms of u and v, and y is something in terms of u and v. So I guess you can say g1 of uv, g2 of uv. And it's asking you to take the partial derivative of this in this sort of matrix. Excuse me? Yeah. Oh, yeah, we're almost done. Sorry, 1 second. And essentially, you just take the determinant of this, and you should get a, root v factor, 1 on 4 root v factor, and then you'll be done. Okay, well, this is literally the last slide. So just one thing to mention. There is a good approximation for a function of a random variable, but only for the sample mean, really. If you have a sample mean xn, and you take a function of it, g of xn, it will tend to a normal distribution with these results here. So this was in the class test, should be pretty chill. And yeah, so that should be it. Thanks for coming, guys. Fill in the attendance form if you haven't already. Sorry? Yeah, it should be the same.
will be posted on the website. Check out that.
They're from like class Ds.
Yeah, they're from like check out resource website. That just gets like 2022, I think.
I'm not sure where they got these. They're from like
Last year.
probably from the Facebook.
We use Math. I don't know.
Please take a look.
Oh wait, the ones
Oh, it's on the Facebook. Read everything.
No, I'm not in that.
Oh, you just joined it this place.
Oh, wait, how much time? I don't really know this one.
You have to choose.
Yeah. Wait, it's in Chinese though. Wait, okay. Can we solve all? There's a way.
That should be what you searched.
Okay. Oh, and you said like this. Sorry.
Yeah, so if you go in the announcements, it's the solution.
Oh,
So there was 6 of them.
okay.
Are these yours? Oh yeah, these are, yeah. Move them there.
And you said, sorry, you said the slide on the website.
Yeah.
What website?
The University of MathSoc website.
Oh. Okay.
Do you want me to just send you?
Alright, it's not here, okay.
You mind doing that outside? We have a tutorial now. Hello. Joshua, you look ready for the exam.
Me?
Yeah.
Good.